Okay, our next speaker, who's miking up at the moment, is Chris Leonard. He's with Verizon, and he's a first-time speaker at our event and a first-time attendee at our event. So try and take it easy on him. He's got a really cool topic this year that we haven't covered in previous versions to talk about 6PE and such things. And so we're really lucky to have Chris come out and talk a little bit about that from a service provider perspective. Maybe. Sorry, I got to get the mic turned on. But we're going to look at this from a service provider standpoint instead of maybe an enterprise perspective. So without any further ado, we'll talk with Chris here.
Can everyone hear me okay? Okay, I think we got it now. Again, as you pointed out, first time speaker, first time at this event, so I'm sure I'll get all the tough questions. And be sure to ask me that one again about multicast. Not sure if I can answer it, but I do have some thoughts to put forward. So again, my name is Chris Leonard. I'm a senior network architect at Verizon. In my role, I take requirements and I build configurations, and I'm usually most comfortable in front of a computer and doing the hands-on stuff. So in this presentation, I wanted to take that perspective and give it to you so you're learning 6PE closer to as if you were configuring it yourself. So first we'll just start off with a brief definition. Then we'll jump into more of the technical pieces of how 6PE works. And I want to start with building off on BGP and MPLS, which are really the core components of how 6PE works. Then we can jump back up to a little more high level and talk about a handful of use cases. Then we'll move along and touch on 6VPE, which is related to 6PE, obviously. And this is more of a customer environment where you need to have separated routing tables. We'll get into further network evolution, and then we'll jump into a summary and then do questions and answers. So starting off with, what is 6PE? What am I talking about here? Well, very simply, it's a technology that leverages MPLS and BGP to tunnel IPv6 across an IPv4 only core. Or maybe I can expand that to say you may have IPv6, but generally you're utilizing IPv4 in the core to take care of IPv6. This is somewhat similar to layer 3 VPNs, also called BGP MPLS VPNs. It uses a lot of the same basic mechanisms, but I'll go over some of the things that differentiate 6PE from this. And it's easily added to a BGP MPLS network. So you only need to create minor configuration tweaks at the edge of the network. It's very hands-off in the core, which could be advantageous for a number of reasons. And customers on the edge, they don't even need to know that you're doing 6PE. They can use whatever they want to get IPv6 to your edge router, and then you can take it from there. And in contrast to layer 3 VPN, you don't have any virtual routing tables. It's all in the global table, in the global IPv6 table. So now I'll dive into how 6PE works and how it layers on BGP and MPLS and some of the configurations to get that going. So the first thing I want to talk about is multi-protocol BGP. And this is an extension on BGP, and it's what allows you to send anything but IPv4 using BGP. This is what extends it, so you have your VPNs, your multicast VPNs, and your 6PE. So I think one of the most important concepts of this is the next hop attribute. And this is a path attribute that's also in the MP reach NLRI, and you'll see later on that it only exists in this additional MP reach network layer reachability information. But this is important because it's how or where this traffic needs to go. You could be carrying whatever information you want. In the case of this presentation, you're carrying IPv6 information, but it only cares about getting it to that next hop that's in the next hop attribute. And another important part of the MP reach NLRI would be your address family indicator or identifier and your subsequent AFI. One other thing that BGP can do that's essential to VPNs and 6PE is it can carry a label within the NLRI, and this is attached to the IPv6 prefixes. And another, not really an essential concept of BGP, but I'll be using it in some examples, is route reflection. And you can do this per address family. It doesn't have to be, if you want to do 6PE, then you have to convert your global IPv4 table over to use route reflectors. It can be done more in a granular fashion. And also it can be a separate dedicated router. And we'll see some use cases where you'll want to do that, but it can also just be the 6PE configurations can be part of your regular router that's just carrying the global internet table, for example. And I'll make the note now that BGP is your control plane, and we'll kind of get into what the control plane represents and how it contrasts to a forwarding plane. So the other part of it, you have two major protocols with multi-protocol label switching. This is kind of the other half of what makes 6PE works. So you have, these are the two common ones, Resource Reservation Protocol. Usually it's called RSVP-TE, and using TE just to distinguish it from the original protocol it's based on that's not really used, that was in contrast to diffserv for QoS functionality. And then another very common one is Label Distribution Protocol. And depending on the flavor of your backbone or core network, or just any network in general, would set up whether you want to use RSVP-TE or if you want to use LDP. And really the rule of thumb that people will say is if you're just trying to use MPLS in your network, then use LDP. But if you want the additional benefits of traffic engineering, such as resource reservation or fault, like fast reroute fault maneuverability, I'll put it that way, then you'd want to use RSVP-TE. And these can both be used together as well if you want to. You can either have them run parallel and only certain traffic uses LDP and only certain traffic uses RSVP-TE, or you can actually tunnel LDP over RSVP-TE. And you'll have label bindings for all prefixes, or you can add policies that allow bindings to only a subset of addresses. And I think this is, when you have a subset, is probably more the common use case. So if BGP is your control plane, then MPLS would be considered your forwarding plane. So getting more into the control plane and forwarding plane concept, this isn't necessarily academic. I don't know how many books you'll find that really call out this specific concept. It's something that I like to use, some of my colleagues like to use to describe the interaction between certain routing protocols and other protocols like MPLS that are used to actually get the traffic across the network versus what is sharing that information on maybe either side of the network. So in your control plane, you have BGP carrying the full routing table or maybe a customer table. The BGP next hop can be a loopback of a router. This is a very common way of doing it. And you can use the external route reflector or hop by hop. And to tie it to 6PE, the control plane is what's carrying the IPv6 information. So for the forwarding plane, you'll have an interior gateway protocol. And this can be whatever you want, EIGRP. Very common in service provider networks, maybe ISIS or OSPF. It really doesn't matter. And this IGP is carrying your loopback information. So the loopbacks, or they may be your router ID as well. It doesn't have to be, but these must be in your IGP in order for this concept to take hold. And in addition to the IGP, you have a label binding for each loopback address. And this is just part of carrying the IPv4 information in 6PE. So this is, again, taking that next hop and getting the packets across the network using the BGP information. So here's a diagram trying to illustrate what I just talked about. So you can think of the orange more as your control plane, and you can think of the blue more as your forwarding plane. So the BGP protocol is communicating with a route reflector, and in this case it's only IPv4, just to put that out there. There's no VPN in this case. This is pretty much just a plain old backbone network just carrying IPv4. So the address on the edge router towards the right is being communicated by BGP through the route reflector to the edge router on the left. And you'll see the important information that I highlighted at the top. You have BGP carrying that prefix, and then also you have the next hop, which is, in this case, the loopback address. And that's what you see labeled at the bottom of each of these routers. So then you have your IGP, and that's highlighted in blue, and that's sending that loopback address across the network. Also, there's an MPLS label, in this case let's call it LDP, corresponding to this specific address that's being sent hop by hop. Each router will allocate a label, and then it'll share it back towards the upstream router. And in this case I have label 3, just an implicit null. There's also 0 for explicit null in case you're trying to preserve some QoS information, just calling that out. So then at the bottom, from the trying to get to that prefix, the router on the left can then send it to the next hop. The IGP information tells it where to go in order to get there, and then within the forwarding plane, through like Cisco Express Forwarding, for example, it'll have a binding to basically say, okay, this prefix, you're actually using a label. It'll push that label, then at the next core router, it'll do a swap operation again that's being held in the forwarding plane of your router. And it'll continue sending that all the way to the edge, where then it can receive this information. So in this case, you don't have any BGP information, you don't have any control plane information in the middle of your network. And this is going to be important when you're considering how to get IPv6 from the edges of your network or to the other side of your network without really having to do anything in the core. So here are the core components of 6PE that tie into what I just discussed. So one thing is you have the address family identifier of 2. That's pretty easy to remember, 1 for IPv4 and then 2 for IPv6. And in this case for 6PE, you have the subsequent, the SAFI of 4, which basically means labeled BGP. And this isn't unique to IPv6 at all. If you had the AFI of 1, you could still have a SAFI of 4, and that simply just means it's carrying labeled information. One thing with 6PE is you have to tell it explicitly to carry this label. Those of you familiar with Layer 3 VPNs, it's kind of included in the address family that you're using to communicate that. So you also have a label within, again, with the label BGP, you have a label within this same MP reach NLRI. And there may be several IPv6 prefixes, but one thing you'll notice is that there will just be one label for each of those. So you'll just have one label value for a whole list of IPv6 addresses or prefixes. And also this is distinct from the IGP label. They have nothing to do with each other. You won't see any duplicates or anything like that. Also, when you're using 6PE, there's a special syntax for the next hop. And I actually kind of like this. It's a very simple address. It's just all zeros up to 4 Fs, and then you have the IPv4 address directly mapped into it. And this and also the AFI SAFI information, this is what tells the router to say, okay, you're not going to use a regular IPv6 next hop to get there. Even though it's technically an IPv6 address, you're going to use your IPv4 table and information in order to get this traffic across the network. So here's that same diagram, although modified a little bit to kind of show what I just discussed with the introduction of 6PE. So again, you have a prefix that's on the right side of the image that's being advertised to the left side, and the left side wants to get this traffic back to the right side. So in the next hop information, now instead of just having that IPv4 address, you have that IPv4 address mapped into an IPv6 address. Also, you'll notice in the BGP header is now it has a label of 500. The corresponding forwarding information, the IGP and the LDP or RSCP labels, that all stays the same. When you introduce 6P into the network, it's not like your network has to reconverge or resend all its labels. That all just stays the same. So in this diagram, I just went ahead and left it all the same. That doesn't need to change. To get to 1.1.1.5, when you introduce 6PE, it'll use the same labels. So now you also see the difference that you have a bottom of stack label as this BGP label. So as it moves through the network, it's using this IPv4 information to forward the IPv6 header across the network. The core routers don't even know that there's this additional router at the bottom, except maybe it'll see in a stack in some database that says, you know, here's this label down here, but it doesn't care about that. It's just swapping that top label to get to the other side. Eventually it'll be popped, and then the 500 will carry all the way to the edge router, which then it'll pop that, and it'll do another lookup. And there's some slightly different behavior in the forwarding database, depending on if you're running or you're doing aggregate addresses or things like that. It'll show up a little bit differently. So in here I wanted to include a couple configuration examples, and this is pulling it from the edge router and also the route reflector. And this is coming from something that I actually mocked up. I did change the addressing a little bit just to make it simpler for discussion's sake, but this is based off an actual working configuration. And also I think XR, at least for service providers, is a good example because that's becoming more and more common in that type of network. And then also Junos is very common in there as well. So starting with the Cisco side, there's a couple key things that actually activates the 6PE protocol. So one thing is you have your normal IPv6 unicast address family information. You're configuring all your prefixes or redistributing into BGP or whatever. But you have to add that allocate label all, and that goes back to when I said you need to explicitly tell BGP that it needs to carry this extra label. And also, instead of using address family IPv6 unicast, now you're using labeled unicast as a keyword. And then that, again, is what tells the router, okay, I'm going to use my v4 information to go across. When you specify labeled unicast, that is 6PE. I haven't seen any other cases where you configure labeled unicast, but you're not doing 6PE. And also, to note that the neighbor is still an IPv4 address. You're peering with an IPv4 route reflector. Again, in Juniper, it's pretty simple. I think you could even consider it simpler than Cisco in a way, where all you need to do with everything else could already be configured. You can have your INET4 carrying your IPv4 information already configured, but you're just adding this label unicast and explicit null to the same group. You don't have to have separate groups or anything. So it's a very streamlined configuration. And that also included some extra route policies or export policies or whatever, just to add a little bit of context into the configuration. So here's an example of what you would see when you're looking in the router. So you have an address that's advertised locally. That would be the AC address. This would be the router in the example on the right. And then also you have one that's learned from somewhere else. So there you see that quad F address along with the next hop. And that's in the routing table. And then also with Cisco, you can view the BGP table separately, and that's what this bottom example is, where you have, again, that locally advertised and also the one that's learned from the other side with the BD route. One thing that I thought was kind of interesting is that in Cisco, in the routing table, they include the quad F, but then in the BGP table, they don't. They actually abstract it back to just the IPv4 address itself. I thought it was kind of interesting. So here's the same thing on Juniper. One thing they do is they don't have a separate table like Cisco does. So you'll notice in the previous slide where you're doing show BGP IPv6 labeled unicast rather than unicast, there's a separate table where in Juniper you have the same table, and really the distinguishing feature is the next hop, where there you have that quad F address and the IPv4 next hop mapped into that. And then again, you see all the information like the router ID, all remain as the IPv4. So this is from a different lab topology. I didn't have any Wireshark capture for mine, but it was a similar setup doing similar testing. But this kind of shows what's on the wire and what BGP is actually conveying. So it's kind of starting from the top to the bottom. Within your path attributes, you now have this new MP reached NLRI path attribute. You can see the AFI of 2 and then the SAFI of 4. So when you configure this BGP, we'll make sure that these capabilities exist also using that information. Then you have the all-important next hop network address. In this case, is embedded within that MP reach NLRI path attribute rather than being a separate one as you would have with just plain old white bread BGP. Then within the NLRI information, you have a list of prefixes. In this case, it's a bunch of /128s rather than, say, like a /36 or 64, 48, whatever. But each one has the same label. So in this example, you can almost think of the label as representing more the protocol next hop of the BGP header rather than each individual prefix. So now we'll kind of jump back out to look at some 6PE use cases. And why would I want to put this in my network? So one, and this goes way back to something that Verizon actually needed it for. And this is when a customer, they come to you, they say, we have an IPv6 mandate, we really want to get over to IPv6 immediately, but maybe your entire network isn't ready for it, or where they're connecting isn't ready for it. Well, then this is a good way to get quick end-to-end reachability. So again, simple edge configuration for the end-to-end IPv6. And I'm kind of stressing that this is really hands-free in the core. Only the edge routers are aware of it. And as you saw in the configuration examples, there really are only minor changes needed to BGP. And this could just be as simple as adding a new address family rather than having to add a whole other group, or if you already have IPv6, you don't even need to add the basic configuration to get IPv6 redistributed into BGP. And then customers also can use native IPv6 or dual stack or whatever they want. And then one key disadvantage of this, it's only rapid if you already have BGP MPLS in your network. So another case, and these may overlap a little bit, but here's a situation where you have absolutely no IPv6 in the core of your network. Maybe that's because it was a rapid deployment scenario, but also it could be you either don't want to put it in there, or maybe you can't. You could have a couple roadblocks. You have outdated hardware, outdated software. And as some people alluded to earlier, you don't necessarily make money with IPv6. So it's sometimes hard to justify upgrading routers in the middle of your network just for IPv6, or maybe you want to wait for some other feature to come along where you'd want to actually put in new routers or go through the pain of upgrading software through all those. And the advantage of this is it reduces the scope of IPv6 work. Again, only on the edges. And then 6PE will provide that tunneling for IPv6 to get through the middle of the network. Here's another scenario that we actually ran into. And this is, I think, a good case where 6PE, even though it's been around for a while, it's a situation where you kind of step back and say, okay, well, we can't do what we did before. Maybe 6PE would be a good case to help. or a good method to get around this issue. So kind of some background of what a BGP-free core is. You're really only running LDP or RSDPTE. Maybe you're doing segment routing, but basically it's just a simple MPLS network. And you're doing this because you want to leverage hardware that's cheaper. You don't have to pay for certain cards that would have more memory where you have to store all this BGP information. So you're really only using a small amount of memory for your labels, for one, but also your IGP information. And again, it's a very small amount of IGP information. You're not advertising everything. Maybe you're just advertising your loopbacks, you're binding those labels to the loopbacks, and that's really all you need to forward the traffic, whether it's IPv4 or IPv6 through the network. And in this topology, you definitely need to have route reflectors, and that's kind of the point. You're trying to get BGP out of the core, and you can buy, and this is even a good case for NFV, which came up earlier, where you can take that piece of hardware, you load router software on it, and you have a route reflector. You don't need a large service provider router to do route reflection. You basically need a server. That's all you need is just memory and processing. So with BGP-free core, this is a challenge for both IPv4 and IPv6. Without MPLS or something to tunnel that information, your traffic isn't going to get very far. It's going to do the lookup. It's going to fail as soon as it gets to that router because it doesn't know anything about where you're trying to send this. So I say that MPLS is necessary for IPv6, but, well, it's actually for IPv4 as well. So again, 6PE is what's being used to tunnel to IPv6 using the IPv4 addressing and MPLS. And this, going back to the diagram I first showed, there's a v4 case where that could actually be considered a BGP-free core. So that's most of 6PE. One thing I also wanted to touch on as well is 6VPE, which is related to 6PE. And you'd use this in a situation where you have a customer where you want to have discrete routing tables, just like you would with Layer 3 VPN. So 6PE is in the global table, but this is where you have your strict customer setup. So this uses something a little bit different than you use with 6PE. That's just regular multi-protocol IBGP, where in this you're using the VPN v6 multi-protocol IBGP. And this is where you have the SAFI of 128, which basically means VPN. So you'll see the same thing for Layer 3 VPN, where it's an AFI of 1 instead of 2, since it's IPv4. And then this introduces your route distinguishers and your route targets. The route distinguisher being what makes it address unique in case you have overlapping space. Probably wouldn't be an issue in IPv6, but obviously it is in IPv4. And then you have route targets that says these routes are labeled this route target. At this site, I'm only going to import these route targets, and at this site, I'm only going to import these route targets. And that's really where you get a lot of your control to keep one customer separate from another, or how you keep a centralized site to get everything within your edge sites, only get a handful of whatever routes they actually need. So again, this is a very similar concept to IPv4, BGP, MPLS, Layer 3 VPNs. So what are some alternatives to 6PE? Well, the first one would be pseudowires, also called any transport over MPLS. This is a term that Cisco uses. But here's a case where the backbone doesn't need any IPv6. And pseudowires are generally used when you're trying to, it's almost like you're extending a wire from site to site. All of the information from the customer side remains intact, even the VLAN information, for example, when they're doing some sort of Ethernet. The problem with this is it's not very scalable. You can imagine just like a spider web of pseudo wires going across the network, just like if you had to run cables between each side. It's really not manageable, and you'd really only want to use this if you have a case where you need to get IPv6 reachability between, like 2 sites, no more than a handful of sites, or else you're going to get in trouble real quick with trying to configure and maintain all of that state. Another thing you can do is you can tunnel the IPv6 information through just a regular old layer 3 VPN, a BGP MPLS VPN. In this case, the customer edge router is the dual stack router. This puts more burden on them, obviously, and it may not be an acceptable solution. They may just want to send you the IPv6 information and let you handle getting it to another site. And the CE also needs to create a tunnel for the IPv6. So they're dual stack, but then what they send to you is only IPv4. And they can use whatever method they want, being GRE 6 to 4, any host of tunneling protocols. And this is one that I don't have as much experience with, which is tunneling IPv6 over ROCP-TE. There are a couple of ways of doing it. One is a 4-ring adjacency where you have your IPv6, and this isn't ISIS or OSPF, but you have your IPv6 topology, and you're using ISIS to basically make that tunnel look like a physical link. And in that case, just like it's going over a physical link, the traffic will go over this ROCP tunnel. And this may have the added benefit of you get all the capabilities that traffic engineering brings. You can also use static routes or maybe some other mechanisms to get the traffic onto that tunnel. Another disadvantage of this, just like pseudo wires, is you're basically building individual end-to-end tunnels where compared to all of these 6PE, you're just building that BGP configuration on the edge and kind of letting the protocols take care of building those paths end-to-end throughout your network. So where do you go from 6PE? You have it in your network, it's working, but you may not want to keep it that way. So one that is starting to finally make it into vendor code would be LDPv6. So in this case, you're kind of going back to the concept of you have dual stack, just like maybe you had with native IPv4 and IPv6. You have separate forwarding for each protocol, which could be advantageous. It really depends on your network and how you want to operate it. One thing that LDPv6 does is it builds on top of whatever transport protocol that you already have in place. So today, obviously, if you have LDP in your network, you're just building it between IPv4. Any hellos, all the label binding information uses that transport session. For IPv6, you're still using that same transport session. Now, there is the option to convert that session over to IPv6, but if you already have it built in IPv4, you're probably just going to add that additional configuration so you're only sending the label bindings and the hellos over that same transport session rather than going through all of the trouble to change the address that LDP is actually using to communicate. Now, this bottom bullet for LDP is, I thought was actually kind of interesting. This is in the appendix of the IETF draft. But they say it's somewhat undeployable in existing production networks. And I have not had a chance to put this in a lab. Again, the vendor code is now just starting to rolled out, and in a multi-vendor environment, you kind of need all of your participants to have LDPv6 ready to put in the network. So what this is referring to is when you activate those v6 bindings and hellos, you add that configuration, it may reset the session. And depending on the topology, that could cause problems. So it could be one of those protocols where you need to reserve it for when you're doing something greenfield or it's in a network that isn't critical. It's okay if there's a little bit of lossiness while you're doing this. And in most service provider networks anyway, you do this during a maintenance window. And there's always going to be disruptions a lot of times, no matter what you do. Even adding an address family to BGP will cause it to bring the neighbor down and then back up. The same draft also does talk about some mechanisms in order to help with that issue of the bouncing session, where they can do a check to basically make sure that the other side is ready for it. This may be getting more into vendor-specific implementation rather than something standardized, so you may need to be careful with that. But essentially, it would allow you to make sure it's on both sides and hopefully keep the LDP v4 session up. So as you're adding v6 information, at least the other side of the network wouldn't even know. It doesn't see a blip in any of the communication. You also have RCP v6. You kind of have to ask yourself, why would I really want to go to RCP v6? You already have RCP v4 in the network, and the distinguishment I'm making here is that you're using, kind of like an LDP, what addressing are you using to set up the session? So with v6, you'd be using v6 addressing. You could actually deploy v6 and maybe have just v4 run over the v4 tunnels and v6 over the v6 tunnels, but kind of like in the other use case I mentioned, you could actually just put the v6 over RCP v4, and that may be advantageous just because you're not adding that extra state to the network. So one more thing to consider also is maybe you want to keep 6PE for as long as possible. This is kind of that if it ain't broke, don't fix it mentality. You have it running, your customers are happy. Why would you want to go in and break that? And one disadvantage that you could maybe call out for 6PE is that you're hiding what your IPv6 traffic is actually doing, because it's basically embedded into IPv4. In the core of your network, it's hard to tell exactly how much there is or how much it's shifting. That may or may not be important to you. And you also only have control of IPv6 on the edges, so that's any policies, whether in BGP, any access lists. It's only there, and basically once you send it across your network, you can't do anything with it until it's on the other side. You know, I do kind of realize that a lot of people are talking about things that are trying to get us to IPv6, or maybe in this case, this is a method of keeping IPv4 in your network just a little bit longer. But at the same time, the reality is it may be hard to get a network that already exists, especially one that has 3,000 routers in it. How easy is it to migrate everything over to IPv6, especially when you have a lot of IPv4 customers? With 6PE, you can still have everyone on the edge talk IPv6, but you still have your core of the network using IPv4, and you're only burning your address space there to handle, basically it scales as big as your network is. Maybe it could be close to as you have 3,000 routers, so you're only worrying about 3,000 loopbacks and then all the IP addresses for the links, which is pretty small compared to what's out there today. So as a summary for 6PE, again, the control and forwarding plane, and going back to some of the early discussions as well, control and forwarding, just as a concept separate from 6PE, is probably going to become a little bit more obvious when you start looking at the SDN use cases, where your control plane is all these servers that are centralized, like your PCEs and things like that, that are basically telling your simple forwarding box what to do. So then you have a forwarding plane that literally is just forwarding. It doesn't really have very much communication with anything, any other forwarding boxes. It's all just kind of going back to the mothership to see what it needs to do next. So again, it's leveraging multi-protocol BGP, and it's utilizing the AF5 and 4 for the SAFI for labeled BGP. It uses that quad F address with the IPv4 mapped into it, and that's used as the next hop for BGP, and the best practice is to use a loopback for that. Then again, the forwarding plane side of this is the MPLS and IGP is used to carry that IPv6 information through the backbone. And I've harped on only minimal configuration on the edges. I kind of want to also expand that a little bit to, just because it's 6 provider edge doesn't necessarily mean that this has to be a service provider. This applies to maybe even an enterprise network where you could have a lot of access or edge routers or whatever you want to call it that are connecting data centers, or it's a service provider network where you have a lot of customers that are going up to these edge routers. And in a large service provider network, you could have a couple thousand of these easily. So do you really want to configure 6PE on 2,000 routers, or do you maybe want to go to one layer higher where you could have an aggregation layer before you actually get to your actual backbone? So in that case, you can put 6PE on that aggregation layer, and that could be down to, even if you have 2,000 routers, it could be down to something like 100 routers, which really, really reduces the scope of work, which is very important to operations teams. And I don't know how many in a service provider at least actually still would go in and manually configure each router, but even utilizing scripts, it reduces the amount of maintenance windows you'd have to open up in order to configure this. And if your aggregation routers are a much smaller amount, then it could be done in one window instead of maybe 10, and it takes several months to get it fully rolled out. And then between those edge or access routers and the aggregation routers, you can just do what you were doing before, or something simple like dual stack. And then you're just handing it off to the aggregation router to actually do the 6PE functionality. And then again in your core, just like everything else, you have no IPv6 or a limited amount of IPv6, and you're using 6PE to get it across. And then again, this really is a bolt-on for BGP MPLS networks. That's the real advantage of using 6PE. So there's definitely a strong case to use or look at 6PE if you have a BGP MPLS network. And maybe 6PE could be attractive enough where you'd actually want to roll out BGP MPLS. You may already have one or the other in your network, so it might not be that much to get it set up. So just some quick advantages and disadvantages. I'll start with the disadvantages, and feel free if you guys have already looked into 6PE, maybe you have some more than what I have. I mean, one thing, and if you want to call it a disadvantage, you may be stuck with it for a long time. If you really are bent on trying to get as much IPv4 out of your network as you can, then 6PE may not be a good choice, because you get it out there and then you'd have to find another solution in order to get those last little bits of IPv4 out of the middle of your network. And it may not be worth it to deploy it if you don't already have BGP and MPLS. So one of the main advantages of 6PE is that it's very mature. It's been around for almost a decade, and even the drafts existed since the early 2000s. So there's been a lot of deployments. A lot of people know about it. There's a lot of documentation, and that's one of the things that makes 6PE attractive to us and probably a lot of other network operators. Again, easily added to your BGP MPLS network. It allows for flexibility at the edge, so you're doing 6PE, but again, as long as you have that IPv6 table, the edge can do whatever it wants, dual stack, tunneling, just get the IPv6 to me. There's less work in the core, and compared to some of the other solutions, I believe 6PE would be much more scalable, especially to something like pseudowires, or where you have to go in and build different tunnels. And one more thing that may help with adding it to the network is it can coexist with native IPv6. If you already have IPv6 configured on your uplinks, you can actually add 6PE. And I know for a fact that Cisco will do this. It'll prefer the routes learned through 6PE rather than if you have any other routes that are being advertised from a previous installation, and you're migrating to 6PE and you already have something else, it'll look at that labeled unicast table and will say, I'm going to use these BGP routes rather than just the plain old ones that you had before. Well, thank you for your time. Let me know if you have any questions. I think I have one in the back corner over here.
What is the impact on the MTU going through the network? Are you increasing your core MTU size, or because it looks like there would be a lot of smaller packets arriving at the customer's premise?
Yeah, so with IPv6, you do have separate MTU rules. In the case of, in the core of your network and how it impacts IPv4, you are adding that label. So if you're running a very tight MTU, you do have to account for that. And for the best practices that I've seen, it's usually best to go well above what you think you would need. There could be some limitations due to transport, like older SONET networks, you're limited at around 4,500 MTU, but you can obviously go up to a jumbo MTU. With any of the native IPv6 from an endpoint perspective, I guess if you're going from just a regular native network and then you're transitioning to 6PE, I'm trying to think if there would be any impact. And I don't know, maybe you've seen that before, but the application could resignal using the path MTU discovery. Yeah, well, with IPv6, in the middle of the network, you can't fragment, so.
For internal protection with the BGP, are you implementing RPKI, or is that really not on the table?
There's been discussions of it. It's kind of separate from, we already have BGP in the network, so it's any discussion with that would have already taken place aside from 6PE. I haven't been involved in those as much, so I'm not really the best person to answer that, unfortunately. Thank you for your questions.
First, thanks for bringing up LDPv6 and RSVPv6, because I gave a presentation here 3 years ago. It was pretty academic on 6VPE, and at that time that didn't exist, and I know Cisco has that out or starting to support it, so that's kind of interesting. I haven't thought about that in a while, so thanks for bringing that up. And that was just kind of a comment or something to think about maybe on the disadvantages. And I've always been a fan of native dual stack. A disadvantage might be you're inherently tunneling V6 traffic now, so there's probably some operational maybe challenges and things like that come along anytime you start tunneling traffic.
Yeah, and I'm glad you brought that up. First, going back to the LDPv6 comment you made, I did have some discussions with vendors, and they took it back to IETF, but one thing I proposed was having separate transport sessions. There really is no reason why you couldn't. I think they wanted to keep it consistent with ISIS, where you might have V6 and V4, but you're still using the same transport session to convey the V6 versus V4 information. But it would be more ships in the night if you had the separate IPv6 session to do those hellos. You don't even have to worry about, will this impact IPv4? Because it's almost like you're building LDPv6 or just LDP in general from scratch. So that was another consideration. I don't know how far they took that, if they're just going to leave it the way they have it now. But really, it's the actual draft itself that says use the single transport session. And then also for your operational case, when you're doing a trace route, I guess depending on how your network is, I haven't seen every single iteration about how you can configure the core, but you're going to do a trace route, and you may get that quad F address if the core router knows how to handle that, or you might just get stars in your network, and if you expose, you don't do like decrement or hide TTL or whatever, a customer may see that and think, well, this guy's network is broken. Or just through your operational team and their troubleshooting, they're not getting the information they need to say, where exactly is this going? So that's definitely a good point of why you might want to move back to dual stack. So thank you.
So another question related to LDPv6. Is it going to be able to do the whole network on V6? And so instead of having ships in the night, everything running on V6? Because actually, when we started out this, we had V4 only networks, and we started to add V6 capabilities to them. We're moving towards sort of ships in the night, and the next step is going to be moving V4 over V6 to make V4 the legacy protocol. And when you want to do that, there could be very good business reasons to do that. One is, if nothing else, to monetize those V4 addresses that you have tied up in your backbone for customer use, when perfectly good V6 addresses will do just fine, and there's plenty of those. So I'll just let you go with that. Okay,
and I've heard of, I think I've seen it called 4PE, where it's the opposite of 6PE, where now, a decade or two from now, you're having networks where IPv6 is dominant. You have new service providers coming up, or maybe they're building additional backbones or whatever, and they do IPv6 day one. Well, with the LDPv6, now you can have that native support where you had with IPv4 and LDPv4. Specifically to the way LDPv6 is now, you could still build those transport sessions over IPv6, but now you're introducing V4 on top of that. Now, if it's greenfield, that doesn't really matter because you're just slapping it in there, and who cares if it goes down because you don't have traffic on it yet. But I think it does facilitate some of that migration where you're going from majority IPv4 and then eventually all to IPv6. And now your service is to say, hey, you still have an IPv4 network, you still have these old servers or this old service or something. Well, we can provide you that connectivity where this new ISP, well, they're IPv6 only. Sorry. Good point. Thank you. Thanks.